Okay, let me sort of give you a little bit of the big picture because as we introduce more and more different notions, it can be a little bit too overwhelming. So the idea is the following. So we have an experiment in a general sense, and then the experiments have many outcomes, and then the collections of all outcomes is S. Okay, but what we had introduced in chapter 2 is sometimes it's not the outcomes that we are interested, but it is the random variable that we are interested. So we have sort of like a mapping. For example, you flip a coin 10 times, and suppose you are just in a game, and if you have more than half of the 10 times, you get heads, then you will win. So that means basically is the overall number of heads have to be bigger than the number of tails that you get in 10. So you will reduce it. Say in this example, flipping the coin 10 times. So the space here, S, is is not small. So it's 2 to the power 10 outcomes. But for each outcome, you basically associate this with 0 or 1. So 0 means you lose, and 1 you mean wins. And so you look at the number, the results of your 10 flips, and then you just count how many heads are there in these 10 flips, and if it's bigger than 5, then you will win. And if you have less than or equal to 5, you lose. This is just one possible, game. Another would be something like I change a little bit. If I have exactly more than 5, I win, 5 heads. If I have less than 5 tails, I lose. But now I think of -1 because I want to introduce one more situations. And if I have exactly 5, so let's look at heads. And if I have exactly equal to 5 heads, then I have a draw. So here, in my second interpretation of the game, or a new game, then I have 3 outcomes. And but the 3 outcomes due to the random variable actually corresponds to the original outcomes, and that we have this. Now, once we have the random variable x, so this stands for random variable. So we will have 2 functions that are associated with it. But the first thing is a little bit, a little bit of a clumsiness. Is we have to think of it as whether the random variable is discrete or whether the random variable is continuous. So there are 2 functions that are associated with a random variable. We call it the small f of x. In the discrete case, we call this probability mass function. And then in the continuous case, we call it probability density function. And then we are going to have another function, which is called cumulative distribution function. And we use uppercase F. And the subscript x is just to remind us that it's coming from a random variable x. So if your x change, I will change the label here. But if the context is always referring to the same random variable x, some people just omit the subscript x here. Now also, this terminology, probability mass function or probability density function, is not universal. Some people just simply call this function, regardless of whether it's discrete or continuous, just probability density function. So they just use the same terminology for both cases. And then some people just simply call it density function. All right? Within this module, but I think this is fairly commonly used, we call it CDF, stand for cumulative distribution function. And again, this is where a little bit confusion might occur. People simply call it distribution function. So all distribution functions are taken to be cumulative. But so these are the very safe terminology when people really spell this out. But then people try not to have so many names, so they simplify the call, the way it is called. But if you come across cumulative distribution function, you know is referring to this. And then for this, now this is just the name of the function, and what are they? The big f of x, the cumulative distribution function, is simply the probability that the random variable is less than or equal to x. Okay, this definition is applicable to the random variable, whether it is discrete or continuous, doesn't really matter. All right, so this definition is applicable to both cases. So that is why in more advanced module of probabilities, our first introduction would be the cumulative distribution function rather than the others. And then now for the discrete case, the small f, okay, and this is uppercase x because we use uppercase to denote random variable. Now, sometimes students, when they first learn it, they are not adhering to certain notation. I'm not trying to be pedagogical, but it is a good habit to, sort of distinguish. So this is a real value, a particular real number that you are talking about. And whereas here, this is a random variable. A random variable is just a way of coding your outcomes to a real number, all right? So this is just a rule, a coding rule. And this is defined as, in the discrete case, is the probability x is exactly equal to small x. Okay. Now, whereas the continuous case is a little bit troublesome. First of all, this does not make sense anymore. Okay, we don't have this. But the small f is actually defined in an implicit way as the integrand of this kind of situations. So this probability density function is defined as the integrand of that gives rise to your distribution function. So that is why it is, of course, this is on the abstract level. It would be actually better to introduce the distribution function first, which we disregard whether it is continuous random variable or discrete, and then and deal with the so-called the density function. Either you call it probability mass function or you call it as this, all right? Now, the distinction is actually not really needed, but it depends on what is your major, what is your background. For students from physics, if they have come across Dirac measure and all this, that you have a single point mass at a certain part, then this actually, because it's a single point mass, that the mass and the density actually refers to the same thing. But so that is why they are able to, sort of like don't think of this. But of course now, when you are doing the integration with the Dirac measure or Dirac mass, then this is not the usual Riemann integration that we are talking about. So that is something that either you use a little bit higher mathematics for introducing the integration here, and then you can get rid of, I always ask yourself whether the thing is discrete and the thing whether it's continuous. Now, at another level, advanced probability, at this module, we only tell you there is only either discrete or continuous. But then actually there is something else here, okay? But we won't deal with it, okay? So this is the scheme we are going to use pretty soon. Okay. So now, for discrete case, how do I get f of x, small x, will be sum all those probability mass as long as your t is less than or equal to x. So here, this is the small x, and then this is the probability mass function fx. So you have some masses here, okay, and this is what we talk about here. So this is so I move away from the histogram. So now what they are trying to, and you might have some of the masses here. So if you fix a x, so you are picking up all the masses up to and including this point, all the masses that you travel from minus infinity up to here, including this point. Suppose there is a mass here, then you have to pick up this point as well. All right. So this is because this is the meaning here, less than or equal to. So if you happen to have something positive at t equal to small x, you have to pick it up as well. All right. So this is how we get from the small f and how to get to the big F. All right. A bit later, we will tell you if I have the big F, how do I get my small f? All right. So this is the part here. And now, this is the discrete case, and this is the continuous case. So the continuous case is actually, you can think of it as you have a small f, and how do you get the big F? And this is through integration. So we are replacing the integration by, we are replacing the summation sign by integration, and this is this. So you are thinking of adding these things up. So if you have a density function, so this is your small little t, dt here, and then now this is your height, fx of t. And so you think of this strip is really, really small. So when you multiply it, you are basically adding up the area under the rectangle. But if the strip is really small, the difference between under the curve for this little piece is almost the same as the rectangle here. And this integral sign is telling us to add them all up, all right, up to here. Okay, now I don't know whether when you learn calculus, why people use these things to denote integral. I think this is a folk law, I'm not sure. The thinking is that it is actually a S, which stands for summation, and then they just stretch it a little bit. All right. I don't know historically whether the integral looks more like this, and then gradually is getting lengthened. All right. So if you are interested in history, mathematical history, I think this is something to. So, but anyway, it's not far-fetched. Thinking of this as a sum, so it's actually corresponding to here. Now, how do you recover the small f from the big F? So my meaning is this: you know this, and how do you find the big F? Through integration. But if you know the big F, but you do not know the small f, this is roughly. Okay. The small f of x is the derivative of the big F evaluated as the same x. So this is the differentiation part. Now there is a corresponding part here. So this is addition, and then there is a corresponding part which later on will tell you subtraction. So in a way, subtraction corresponds to differentiation because the derivative is actually the increment of the y-axis, which is the subtraction, over the horizontal increment, and then this is actually the limit. So in a way, we are not. Actually, we are still doing differentiation, but doing it at a relative manner. The differentiation. Okay, so that is why if you look at the topic, we talk about random variable as a way to code the outcomes, because it is not the exact outcomes that we are interested. It is some function of the outcomes that we are interested. And then we introduce the discrete random variables. And also continuous random variable. Now I will talk about it a little bit later when we come to mean and variance. I have this. So this is a common game called SIGBO or called Big Small. And my point is not trying to get you into this. In fact, a lot of people who are in statistics and probability, actually, we don't gamble. We are poor, academia. But we actually have lost hope of doing this. So now, actually, they give you, it is a very fair play. So if you bet on big, this is your winning probability. And as a result, your losing probability would be 51.39. And so the house will have an edge of 2.78% over you. And if you bet on a particular total, this is how your probability of winning, and so on and so forth. Okay. So this is one. I'm not sure. I use this for my tutorial, not for this module, but I can do it. But I was using this not to encourage. I don't even know whether this is online. You can gamble online. Please don't. All right. Otherwise, your parents will scold me. Basically, you can see they are very transparent. They are not out to cheat you, by making you ignorant, but actually, once you get into the habit, is what they want. So they give you a payoff, all right? This, I think, depends on how much is actually collected. Now, in fact, they will never lose because they only, after they collect, say, 100 million, they only use a portion of this for the payoff. So they won't overpay you by what they have collected. So they are very safe, all right, unless some government busts them. Okay. Anyway, so this is a payoff. Now, one thing that is interesting, the wage for betting this, I suppose, I didn't quite read it. I think it's $1. When I was doing this, at a particular juncture, they actually give you what is the jackpot, I mean, if you win. So I was able to compute for every $1, what is your expected payoff. Your expected payoff is actually 25 cents for that particular, I think it's around there, meaning that they pocket your 75% for every $1 that people bet, all right? So it is very deep pocket. Would you mind going to buy a sandwich and then the thing is only 25% of what you're paying? Maybe you're willing, right? I mean, maybe at Starbucks, I think a glass of coffee is $5, but maybe it only worth about $1. But anyway, you have people to serve you. So this is this. Okay, I will come back to this. But one thing that I want you to notice is the design of the thing. The design of the thing is that you will win small money with quite reasonable probability. Say, for example, you will win $2 every 1 in 40 times. So when you bet often, you do win small. And then that would make you think that winning big is coming, all right? And this is fat hope, all right? And so basically, the design is, when we talk about it, the mean of the whole thing is actually negative, and it's negative 0.7 something. But there is a fairly good proportion. If you add up this probability of, say, winning small money, it depends on your definition of small, maybe $10 or below. So you can add up all this probability. This is not still okay. I mean, maybe something like 4%. So if you pay 100 times, you get 4 times to win a little bit of money. Okay. So, but if you only win once in every 100 times, let's say, if I make it up, so you only get around, I mean, maybe $5. But you have played 100 times already, all right? So you have already contributed $100 to this company, all right? So I will come back to it because I wanted to illustrate the meaning of the expectation. And then something more closer to home, I have figured out how much mark I have to award if my other lecturer agree in the multiple choice questions. To be fair to you and to me, will be if you get a wrong answer, I will deduct 1 mark. If you get the correct answer, I will give you 4 marks. Then the expected value would be 0 if you purely by just trying your luck. All right. So so that would be the way I assign the mark. Now here, we are introducing the cumulative distribution function. Okay, so that is a definition. But the main definition that you have to watch out is this is less than or equal to. The equal sign is crucial, all right? Now, the equal sign is crucial especially for discrete random variable. But for continuous random variable, it doesn't really matter, all right? So something that you have to watch out. So note that f of x is a non-decreasing function. And when you have a smaller argument in your function, the functional value is no bigger than the functional value evaluated at a bigger argument, x2. Okay, and this is always between 0 and 1 because f of x is corresponding to a particular probability. So probability can't be negative and can't be bigger than 1. So property B is obvious. Okay, and property, maybe I want to illustrate property A. because it illustrates something that we have learned before. When x1 is less than x2, fx of small x1 is equal to probability of x less than or equal to x1. Now remember, this is just a shorthand notation for these situations. All the x in your random, all the possible outcome, and this is this, okay? Now, but if you compare this event, let me call it A, and then compare it with B here. B is this. Okay, the event B is a bigger set than A because this is a bigger number. If your random variable value is less than or equal to small x1, it follows that it has to be less than or equal to x2. So as a result, this is a bigger set. And we know that bigger event, bigger probability. All right, so we have this. And so this will be equal to, by definition, all right? So what it means is if you are observing how the function big F is, big F has always to be sandwiched between 0 and 1, and that it is a non-decreasing function in this way. So this is one example, but I might have some example that there would possibly. So this is example 1. But I might have something like this. And then there is a jump. And something like this. Okay. So these situations are possible. Okay. So the cumulative distribution function extends naturally to other types of random variable. For this reason, it is sometimes simply called the distribution function. But of course, if you have a number of random variables at hand, then you have to tell people explicitly whether it is a distribution function of x or of y or of whatever. So you have to specify it. But now we only have one random variable, then we'll just call it distribution function. Okay. Now, this is how we moved from the probability mass function. Okay, in our module, sometimes it's the preference of another lecturer. He likes to call it probability distribution, F, but I would call it probability mass function in this module. Don't worry about it because in the exam we will standardize our notations or our terminology. So this is the definition of the cumulative distribution function as it is. And this is the meaning here. And this is why we call it cumulative, because you imagine you are coming from minus infinity and you want to reach up to the point x and at x. So as you walk along the x-axis, whatever mass that you come across, you just pick it up and you cumulate this. All right, so this is this. And then this is just the definition of the density probability mass function, probability of x equal to t equal to this. So maybe it looks a little bit awful. This is actually our definition of the cumulative distribution functions. And this is the meaning of this because you are just picking up all the possible probabilities or mass as you move from minus infinity to the point x and including x. So this is something that is, sort of follow from the probability itself. Then this is just a notation about what is ft, back to the random variable itself. So even though there are a lot of equal signs some of the equal signs have been introduced earlier. So the only thing probably is a little bit new is this thing, all right, is this equality. And so that is why it's called cumulative. The cumulative distribution function of a random variable is a step function. What do we mean by step function? This is a particular step function. Okay, and the y-axis is the cumulative distribution. So it is actually something like this. Okay, depending on the possible values. So I purposely do it this way. And then there is a jump here. And then there is a hole here. And then you go up. Okay, and this is 1. And after a while, you will jump to here, and then you will stay here for good, all right? So this is the what we call a step function. You think of it as the steps that you climb up. And later on, we will introduce this. This jump size would correspond to, suppose this is x1. This will be corresponding to your density probability mass function at x1. And then this is x2. And this portion is your f of x, x2. So it's the jump size, all right? Why do we only look at this? Because this guy is the cumulative one. So up to that point, it adds up the mass at x1, and it adds up to the mass of x2. So you have to subtract this one back, and which will give you this. And this is the jump size here. And so if this is x3, so this would be f of x, x3, and so on. So in my picture, the random variable x only takes 4 possible values, x1, x2, x3, x4. And then the corresponding probabilities corresponds to the jump sizes, all right? And so on. Okay, so this is what I meant by subtraction. So you are subtracting where this point is, the value, the y value of this point minus the y values of this point. So you are doing subtraction, and then you recover back the jump size. You do the same thing here by subtracting the 2 corresponding y values here, which corresponds to here. And you always have a hole at the jump, and the hole is always occurring, on the left-hand side of x1. So we will have x1, a superscript, a minus sign means you are very close to x1, but you are always coming to x1 on the left, all right? Okay. Now this is where the notation comes now. For any 2 random variables, a and b, with a less than or equal to b, you have to watch out this. You have to spend a little bit of time to watch out this, because here the first inequality is less than or equal to, meaning that you include the a as well, all right? And here you less than or equal to b, but is inclusive of b, all right? You have to pay extra attention, because if it's discrete, when it is continuous, it doesn't really matter. So what it says is that the probability of x less than or equal to b minus this. This follows from set theoretic argument, because this is just this set. So this set, x is less than or equal to b or bigger than you, is actually coming from x is less than or equal to b, set subtraction of x is less than or equal to a. All right. So this just follows from this. And so as a result, when I take probability here, and so I take probability here, and now because this is the set here, this is a B here, and this is a A here. B is actually a superset of A. So as a result, this is the same as probability of B minus probability of A, and that is the part there. So, so what we are doing here is not entirely by definition, but it's because we have our chapter 1 at our disposal. So we have this, just now what I have written on the piece of paper. So A minus is the largest possible value, strictly less than A. This is a little bit not a very nice way to put it. It is actually, when I do the calculations, I will come back to explain this a little bit further. The reason why we are not able to use a more precise language is because I think the lecturers wanted to refrain themselves from using the concept of limit here. So, but I guess if we stay on the intuitive level of our limit, I think it is helpful. So we'll get to see this. Another way to think of it is this. When you are evaluating the probability of a discrete random variable, which is between A and B, then you just ask yourself, between A and B, A endpoint included, B endpoint included. Then you just look at the random variable itself, whether it does take A and B. And so, so this is just A and here. Now we are saying that this is integer values. So as a result, we exhaust all the possible integers. Now A doesn't have to be an integer, but this is assumed in this part C. But suppose A is taken to be, say, 1.5, and then B is 2.5, then you can think of it as bigger than 1, right? Or bigger than or equal to 2. Okay, if I use A as 1.5, because it is integer. So if it's bigger than or equal to 1.5, it's the same as I can say bigger than 1 or bigger than or equal to 2, right? So it is really up to us how to describe it if we know the random variables are integer values. Now, if A equal to B, we are still under this assumption, I think. So I think it is not quite, it is a little bit confusing because A, B, C, and D are taken to be separate contexts. But I think here we are following this directly. So maybe you should strike out the D here. And then think of this now is a special case of these situations. When A and B are equal, then X probability of X equal to A equal to the cumulative function at A minus the cumulating function of an integer before. All right? You get my point here? Because I think this statement is following this assumption. All right? So, either you cut and paste this entire statement into here, in front of here, or simply strike out the D, but then think of it as part C actually has two statements. One is about this probability sandwich between A and B, inclusive of the two endpoints, and then the other part would be the two endpoints actually collapse. So this interval is actually one single point. Okay, now this is geometric cumulative distribution functions. So P is a parameter which later on we will have an interpretation for P. P will be regarded as the probability of success, all right? Okay, and then geometric distribution is that you keep trying until you get the very first success, And the random variable x here is counting the number of trials in order to get the very first success. All right? So I think we have mentioned this before. So this is like, you can think of it as a waiting time. You keep performing an experiment. Each time the experiment will lead to failure or success, and you are interested in the very first time that it is a success. And you count the success trial as one trial as well. Okay. Now, and the reason why this is the case is can be explained quite quickly. So, so that this formula is not coming from thin air. So you think of it as, so x is equal to x, meaning we need small x trials in order to have the first success. Okay, inclusive of the trial. So this is small x, and this is trial number 1, trial number 2. So you have this. But this is the very first time you get a success, so this is an S here. And then earlier, it has to be a failure. And all of them has to be a failure. And so the probability of this is 1 minus p. The probability of this is 1 minus p, and probability of 1 minus p. And then this is p. So your experiments, you perform it in an independent fashion. So as a result, this is 1 to the power p to the 1 minus p to the power x minus 1, because you have tried the first x minus 1, and they all lead to failure. And then the very last moment, you get a success, so you have a p. So that explains the formula in your slides. Okay, and so now we want to find its cumulative distribution function. So f of x is an integer, positive integer. And so we are accumulating it up to the x. So what it means is that k equal, I have to add up the probability at 1, probability at 2, all the way up to probability at small x. So this is the notation, the meaning here. K has to be integer. And so I have this. So this is just plugging into the expression of what this is. And now this is now k, not x, okay? So we change it back to k, so it is just a name. We have this, okay? I think I want to remind you of a formula which is called a geometric progression. There is a closed form formula for geometric progression. So the geometric progression is, okay, let T be the total. All right. So I have m terms here. And the relations of the terms are differ by a ratio, okay? So the next term over the current term is always a common ratio, so R. So that is why we call R as the common ratio. So there is a formula for this. It is basically A, the first term, minus the term after the last term. Okay, so you imagine you have one further term here. So this is this. And then over 1 minus the common ratio. And this is provided, this formula is provided this is R is not equal to 1. If R is equal to 1, then you are just adding A m times. Okay, so this is the formula for a geometric progression, what we call a closed form of the sum, all right? And so this is what they are using. Okay, so maybe since I'm here, I fill in the step a little bit more. So maybe it's better that I write it as P plus 1 minus P to the times P and dot, 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 and then 1 minus P to the power x minus 1 times P. So I move away from using the summation sign. Okay, so this is the first term. Okay, and this is our A. And this is the common ratio minus the term after the last term. So which would be P, 1 minus P to the power x over 1 minus P. All right? And so this is the common ratio. So according to the formula, it is 1 minus the common ratio. Is that okay? So first term equal to P common ratio equal to 1 minus P. So I have to 1 minus this. And so as a result, this is the denominator is a P. The numerator has a factor of P, so I pull it out, so I get this, all right? So I hope this is a bit better in this way. Is that all right? Okay. Just a side remark here. Probability is in some way an applied, kind of a math thing. Of course, there are some very probability things is really math, not even applied. But what I'm trying to say is when we are solving a problem, an applied problem, you do not limit your tools. So that's why sometimes we pull out certain things here. And for example, in this particular case, we will pull out the geometric progression, the formula there. So when you're solving applied stuff, we usually have a lot of tools in the toolbox, all right? Okay. Okay, so this is just summarizing what is this. And then maybe I wanted to plot this so that it is, give you an example. Okay, so I'm plotting this. This is the big F. Okay, so it takes values at 1. I think of it 0, 2, 3, 4. But you probably know what I meant. And so thank you. So this is where I have. And now the function stays 0 all the way up to 1, except 1, exclusive of this point. And then I will have a jump. And the jump size is P here. Is it? Yep. Okay. And now I will have this. And so I will have a jump here again. And this is 1 minus P, something like that. you better check, all right? And then I will have another jump. The jump size is getting, I think it's 1 minus p squared, something like this. Again, you check, all right? And so on and so forth. So you always have a jump and so on. Okay. I mean, I don't want to spend time in trying to figure it out. We can do the subtraction there to find out, but then this would be something like this kind of factor. Or I have a p times this. So I think this is p, and then this is this. So this corresponds to the probability. So I think it has to be p times 1 minus p, and then p times 1 minus p squared, and so on. So that is the meaning. From here, we have the passage from a density function moved to a cumulative distribution function. Okay, maybe we have a break here. Then we will have example 4, and then we plot the cumulative distribution function in the coming slides for the example 4, and we will do example 5, 6, and then we'll introduce the continuous case. So hopefully we can finish everything as much as possible, because my counterpart probably will finish the mean and variance by today, so I have to catch up. So let's have a 5 minutes break. So please come back at 11. Okay, so we wanted to continue with some further examples. Okay. I mean, of course, it takes a little bit more effort to explain this, but the reason why I spend time on this because this is going to be one of the common discrete random variable, the geometric random variable. There is a parallel. This is you are thinking of waiting for the very first success, but there is actually a parallel, what we call the negative binomial distribution. If you are not just happy with the first success, suppose you keep waiting until the 10th success, then that would be a negative binomial, and it would be the situations of after the time you wait for the first success, then plus the time you wait for the second success, and plus the time you wait for the third success. So the negative binomial in that sense is actually the geometric distribution is still the building block of the negative binomial. So having this background in mind that you are keep trying until you hit the very first success, it is actually beneficial. On the side here, there is a gambling method. It is called a sure win gambling method. It is called, I think it's a French acronym. It's called Martingale. But if you Google Martingale, you might get very mathematical introduction. The very first version of the gambling is this. You put $1. You does not depend on whether what is the probability of win or lose. It doesn't have to be even half and half. And suppose you have a probability that you will win. So the first thing is you put $1. If you win, the strategy say you quit, don't linger anymore, leave. All right. If you lose the first bet, the strategies ask you to double what you pay earlier. So the second game you bet $2, and if you win, because you have lost $1 before, now you will get $2 back. So you still win $1, and the advice is quit, don't play anymore. Okay. Now if your second game you also lose, which you place $2. The third game you double what you play earlier, so you pay $4. Now if you win, you will win $4, but you lost the first one and the second one, so you will lose altogether $3. So at the moment when you win and you quit, you always win $1. All right? And this is regardless of whether the game you have a very small chance of winning. As long as you have a positive chance of winning, this game, if you really can control yourself, you keep betting whenever you lose. And then each time you double your wage. And your moment of winning will come eventually. And then when you win, you stop. But in total, you will win $1. So this is a sure win strategy, all right? But you be sure if the game is not very good for you, say the probability is, say, 0.4 that you will win, you might have to bring in more capital because the house will not lend you money. I will lend me money, keep lending me money. One day I will win, and then I will return everything to you, and then I will still get $1 back. Okay, so this is in theory, it is. I mean, you can do it, but in practice, you need a very large capital to buffer the situations that you keep losing until your first win will come. So, and this is number one. The number two is in a lot of casino, there is a rule how much you can bet. So if you lose, say, up to 10 times, so you have already lost $1,024. And the casino's rule is that you can't bet more than $1,000. What I have advised you will fail because you can't double your wage to $2,048. So you will become a loser. Don't blame me, all right? All right. So this is the situations here. So this is a purely academic exercise, but it illustrates certain things and then help us to appreciate the plot. Okay, the starting point is we start with probability mass functions. And now all this example is concerning how do we find the cumulative distribution function. So this is the solution here. So basically what you can think of is this. You first sort of like plot this. Okay. So I can think of x, and then at 1, this is 1/4, and then at 2, it is a half. At 3, it is 1/8. And then at 4, it is 1/8. So this is our small f. And now this is our big F. Okay. So I think the slide uses A. So I will follow it. All right. So you imagine this is 1. So these are the critical values. So if your A is somewhere here, and you accumulate the mass up to and including this point, and of course you will not include anything, so your function will be 0. So you keep going until you are actually at just before you hit 1, the function is always 0. But when you are exactly at 1, you will pick up this mass, which is 1/4. All right, and so you will not pick up anything because there is nothing for you to pick up. And then up to here, so 2. And you will pick up 1/2 of it. Okay, so it is ... here. And so you will jump to, this will be 1/4. And this will be 1/2 plus 1/4. This will be 3/4. All right, and so you will stay there, and until you hit 3, then you will have another jump, which is 1/8. So 1/8 will be 7/8. And so you move to here. When you're exactly at 4, you will pick up the remaining 1/8. And so you will get 1 here. And you will stay in 1 forever. All right. So that is how this function f of a is in your slide. According to my numbering, it's 326. All right. So it depends on whether you are feel comfortable with the kind of mathematical notations in the slides, or you think of it a little bit more graphically, like this, it might help. All right. So that explains why I have 1/4. 1/4 is exactly the mass that I pick up at 1, and then at 2, I pick up an addition of mass 1/2. But I already have a 1/4 in my hand, so I have 3/4, and so on and so forth. And so this is the plot here. So this is how we construct from a probability mass function to a cumulative distribution function, and we do it by adding things. So let x be the number of days of sick leave taken by a randomly selected employee of a large company during a particular year. Now, some of these things are of interest. Say, for example, from the management of the company. One way is to increase productivity, is to cut down the number of sick days. And one way is encourage your employees to have a healthy lifestyle, or some company give gym memberships to the employee to encourage them to, exercise, or having a more balanced kind of work and lifestyle. So anyway, the first thing is look at the historical data. Since the company is assumed to be large, there is a large number of employees. So we just use the last year as a way to gauge it. And this is what is happening. So F of 0 is 0.58. So 58% of the people do not take any days of sick leave. And then so this is the extra probability here, which is 14, right? So 14% of the people take 1 day of MC, and so on and so forth. So the first thing we want to handle is to say, what is the likelihood, what is the probability that people take, what is the proportion of the employee in this company take 2 days, between 2 days and 5 days of sick leave, inclusive of 2 and 5. And then B would be x equal to 3. So you will see a little bit of clumsiness when we describe less than or equal to, because we just want to make sure people know I'm including 2 and I'm including 5. So this is unavoidable, but as I mentioned, in our daily life, people may not be as precise, and if you are in doubt or when the situation is ambiguous in workplace, you should clarify it, whether you are including the endpoints or not including the endpoints. So this is the probability of X is between 2 and 5, inclusive of the 2 endpoints, is to calculate the F of 5 minus something just before 2, F of 2. So the little negative sign in the superscript means a little bit as small as possible on the left-hand side of 2. So slightly less than 2. And here, because the function is constant in the interval, except jump at the integer value, so slightly less than 2 would be the same as the same value of the function at 1, all right? Or if you really plot it, you will see there's a hole, and this is the hole that we are interested in, and that is 0.22. All right? 0.22 comes from, you look at the increment here. All right? Okay. So, yep. So you are basically subtracting this number. Okay, 0.94 subtract 0.72. Okay, and then this will be just this. There is a jump at 3. And so what is the jump here? The jump is from 0.76 to 0.81. So the jump is 0.05. Okay. So this is another thing. Many manufacturers have quality control programs that include inspection of incoming material for defects. Suppose a computer manufacturer receives computer boards in lots of 5. 2 boards are selected from each lot for inspection. Okay. Suppose the boards are all distinct. List all possible inspections. Suppose that boards 1 and 2 are the only defectives in a lot of 5. 2 boards are chosen at random. Define X to be the number of defective boards observed among those inspected, and so on and so forth. All right. So you are inspecting 5. You are inspecting 2 out of the 5. So you have 10 possible inspections. And so you have 1, 2, 1, 3, and so on and so forth here. And X is counting the number of defectives. So either you have no defectives, you have one defective, or two defectives. So in this kind of example, the natural thing is we actually calculate the probability mass function from the problem itself. We do not compute the distribution function here, all right? But we know the two things correspond to one another. So depending on whether you think it is more convenient to calculate the distribution function, then you go ahead. But here, this is simpler to do so. So f of 0 corresponds to you have no defective that you can identify during the sampling. So what it means is that now you happen to pick 3, 4, 3, 5, or 4, 5 out of these 10 possible combinations. So that would be 3 10s. And f of 2 equal to that you pick up 2 defective. And so you will pick up exactly 1, 2. And this is 1/10. Now, there is a trick here that is, okay, the trick is because I recognize that the sum of the 3 probabilities here should add up to 1. So, and I would just simply do the subtraction here. Now, this is just the way to go, but another way to go about it is x equal to 1, then you just go over this and then assign the value. So this is x equal to 2, x equal to 1, x equal to 1, x equal to 1, x equal to 1, 1, 1, 0, 0, 0. So all you need to do is to count here. And I think there are altogether 1, 2, 3, 4, 5, 6. So, so you can actually do the calculation directly, and that would be 6 out of 10. And unless this is rather difficult to do, I would recommend you to calculate this directly, and then you can check whether they add up to 1. So this is an assurance that at least, you are not, there is a good possibility that you are on the right track. Okay, so now that we have the probability mass function, then of course it follows that we'll be able to calculate the distribution function. So I'm not going to go through the detail, and it is fairly mechanical here. Okay, now so far we have been talking about the cumulative distribution function for discrete case. It's a little bit annoying for cumulative because you have to watch out whether the endpoints are included or only one endpoint is included. And if only one endpoint is included, whether it's the left endpoint or the right endpoint. So these are little things you really have to pay attention to. But for continuous random variable, the mass that you picked up at a single point from a density will be 0 because a point mass is not possible in a continuous random variable. Okay, so the first thing is we recall the definition of a probability density function. It is what it's saying, first you start with the cumulative distribution function and big F of x from the random variable itself, because this is defined as the probability of the random variable less than or equal to small x. Then if somehow you are able to write down this distribution function as an integral of another function, then this other function, small f here, is termed as the probability density function. I want to emphasize one thing, but this is something minor, even if you don't know, is no cardinal sin here. Probability density function is not unique, all right? So because if you change your density function a little bit, say if you pick a finite number of points and then you just change it, you are not going to affect the integral because the integral over, say, 10 or even a countable number of points that you change it is not going to affect your integration, the area under the curve, okay? Because the area under the selected points where you change is 0, so there is no contribution over there. Now, here, we are careful here. If the derivative exists, I think we have to be a bit because there are two functions that we are talking about, so it means the derivative of the big F exists, all right? So we will have small fx is equal to the derivative of the big F at that particular x. So, so maybe you want to insert this. If the derivative of the big F exists, then we have this. But sometimes it may not exist at certain points, but it would be quite arbitrary to assign it. Again, the derivative at a certain finite number of points is not going to affect us. Now, the interesting thing is, if you have the cumulative distribution function, it is very easy to calculate the probability that the random variable is sandwiched between two endpoints. So this is an interval, AB. Regardless of whether you include A or B as the endpoints in the probability assignment, it's not going to affect you. All right. So there are actually 4 situations, whether you take away the equal sign on the left-hand side or on the right-hand side. There are altogether 4. And here we wrote down 2 of them. All right. And this comes from subtracting this, because it is coming from probability of x less than or equal to b minus probability of x less than or equal to a. This is because I think we have drawn this before. We can represent this as the set difference of 2 events, namely x less than or equal to b and x is less than or equal to a. And since x less than or equal to a is a sub-event of x is less than or equal to big B, then the set minus is, after I take the probability, it can translate to a minus sign there. Okay, f of x must satisfy the following conditions. F of x is a non-decreasing function of x. We have mentioned it in a number of slides before. If you remember, x1 is less than x2, then f of x1 is less than or equal to f of x2. You can't assert that it is strictly increasing function, because the function might be flat. Okay, so like the step functions. The limit here, the left-hand extreme value is 0. All right, if you imagine you keep going to the left to the minus infinity, and you observe your functional value, the cumulative distribution function, this would be 0. And if you keep going to the right, you will approach 1. Now, you may not be able to hit 1 with x that is a finite number. We will have an example that it will never equal to 1. But as you keep going to the infinity, to the right-hand side, it would be equal to 1. I want to add a part C in it, okay, because the way it is set is not correct, all right? When I was looking at this, I was thinking the notes here is trying to avoid the use of limit. But anyway, in part B, it has already used the notation of limit. Then why should we stop at, withholding one part from you? Okay, anyway, I will say this. If any function f of x satisfies the above 3 conditions, okay, part C is coming, simultaneously, then it can be a cumulative distribution function of a random variable. Okay, so we have some random variable that will give rise to this particular big F. And this is the condition of C. Okay, for any x, a real number, limit f of x plus a little bit of things. Here, this is my notation. I will explain this. Will be equal to f of x. So we have a name for this. This is right continuous. And then h is going to 0. exists. And this is actually what we were using as a notation here. So left limit. All right. So this is condition C. What it says is h going to 0, but I use a down arrow, means that h is always positive, but it's getting smaller and smaller. So x plus h is always on the right-hand side of x. So that is why we call it right continuous. So you imagine you are walking along the curve from the right-hand side of x. You will reach the value f of x, which is the value that you assign by the function at x. But if you are walking from the left-hand side of x, because h is negative, h is getting closer and closer to 0, but it's going up. So that means h is negative. So x plus h would be on the left-hand side of x. So you keep following the left-hand side, then you reach the hole, okay? If there is no hole, that's fine. So this is one situation. The function is continuous at x. All right? So it's okay whether you go along here. But the other situation will be something like this. So if you keep going on the right-hand side, you will get to here, the limit. And the limit is actually f of x. But if you keep going from the left-hand side, you will arrive at this point, all right? So which is where the hole is, all right? So that is the limit. Now these are some finer things, but you do encounter it in one specific case for the discrete random variable, all right? So we probably try to avoid, very elaborate limit things, but certain situations we still need the intuition there. Okay, so the cumulative distribution function of a random variable from example 3 is given by this. This is what we call exponential distribution, all right? And it's usually used to model the waiting time of something to occur. For example, for electrical appliance to break down, or for a bus to come, or for arrival of a certain event. So we are doing integration, but the density function in that example is actually this. So the density function, this is small f. The density function is actually like this, all right? And it is somewhat like this. Okay, so here when you construct the big F, it is the area under the curve. So if your x is somewhere here, the area under the curve would be under this curve. And so this would be 0. But if your x is somewhere here, the area under the curve will mean under here for this portion. And then the x will be here, it will be under here. So the contribution of the area is just coming from here. All right? So that is why we have these situations. All right? So the first thing is, now this is my advice. A lot of students are learning probability. You misplace your time management on the integration. Imagine if you set up the integration, the limit's wrong, or your function is wrong, the effort that you do for your integration will be just a mathematical exercise. You're not going to get the right answer. So the crucial thing at least is to really make sure you get the integral form right first, meaning that the limits must be right, and then you pick the right curve to do the integration. Now, even if you can't do it later on, at least you are correct at this point, okay? And I mean, we will give partial credits to it. All right. So at least you are on the right track. But if you are very sloppy in writing down this, no hope that you will get the right answer in the end. All right. So this is time worth spending. So the rest will be just our usual integration of exponential functions. So I assume this is familiar to you. So we will have this. So how does it look like? In this case, there is a 1 here. And so it would be something like this. The function is this. And then this is, okay. I can't quite draw it because the curve is actually getting closer and closer to this line, y equal to 1. But it will never reach this line, all right? So there is a big term here. It's called asymptotes, right, of this function. Okay. So this is the illustration I was meaning before. F of x is never equal to 1, whatever large value of small x is. But in the end, it will equal to 1. Okay. So here, this is the density function. So the density function is somewhat like this, 0, 1, and that it is actually excluding, so it is equal to 2x. Okay. All right. And so we just need to do the integration. All right. So if you change your density function like this, and then I attain value 1 here, the answer will still be the same for the big F. All right. Even though the two small f differ by 1 point, again, your area won't change. So the cumulative distribution function of x is this. And so this is just a matter of integral. So when x is small, negative, your integration from minus infinity to x, you actually on the left-hand side of where the curve is. So the curve of the density function is flat at 0. So you have to use this curve, all right, 0. And then when x is between 0 and 1, you have to break your interval. You're integrating from minus infinity to 0, and then from 0 to x. Okay, so this is, you have to be careful about all this. And then when x is bigger than 1, again, now you have to separate into 3 integrals, minus infinity to 0, and then from 0 to 1, and then from 1 to x. But now the density function for the third integral and the first integral corresponds to the 0 curve. All right. So the main contribution is just coming from here. So as a result, these are the integration. So the integration is somewhat, I mean, in this case, somewhat is easy to integrate. What is really important is to figure out this interval. But for some other density functions, it might be elaborate, so you do need to spend time on it. But if you get this equal sign right, at least this is how far you can go. Whether you are able to simplify the integration would be some other matter. We will not, this is not a math module, so we will not give you some unreasonable integration to do. That is, at least my philosophy is, this is more like a probability class. So let me see. I wanted to finish this, so sorry I have to hold you guys for a while. So let's denote the vibratory stress, PSI, on a wind turbine blade at a particular wind tunnel. And So this is the density function. If I'm not wrong, this is a particular case of a Weibull distribution. So the engineer use it very often. But anyway, I mean, coming up with this form comes from science or from engineering, all right? So it's not, why is it this form? And usually people are able to know the form, but somehow the theta is not known to us, depending on the material of the blade or whatever, or I mean the shape of the tunnel or whatever. So the second half of this module is about estimating the theta from real data. So the way, so people from science principle or engineering principle come up with the form of this density function, and then it involves some unknown parameter, and so usually people use data to estimate the theta. And after estimating the theta, there is a decision level, that is the hypothesis testing. Is that theta equal to a particular theta that you want to use? So you want to make a decision whether this is the right theta. Okay, so the rest is just simple integrations, and just sit down and do it. All right. So it's kind of, I mean, a test of patience. So the integration is very easy because of the help of the x here. Without the x here, it is we know that there is no closed form for the integral. All right. But with an x here, one way you can do that is by a change of variable, x squared over 2 equal to u. And then, so when you do the integration, you can do so. So maybe I'll just mention it here. So you are basically integrating from 0 to infinity. X, I can pull out the theta. E minus x squared over 2 theta squared. So one way to go about it is put let this, okay, and then your du will be x dx. So x dx will give you the du, and then this would be all right, and so this is now back to our simple integration of an exponential function in this form. So I guess I will just flesh this thing out, and so it's just work, all right, but work that you know you will be able to handle it. So maybe a point here is whether it's strictly less than 200 or less than or equal to 200 doesn't really matter because it's a continuous case. So, so this is it. Okay. This is very similar to the one e to the power minus x, but this is going to closer to 1 faster because of a square term here. All right. So, so this is it. Okay, so I think that's what I want, and then Friday we'll talk about mean and variance. So these are what we call the first, mean will be the first moment that we are going to talk about, and then we will have second moment, and so on and so forth. So these are some numbers that associate with the random variable itself.